Hello students. The topic of today's lecture is the residual neural networks or ResNets. But before that, let's have a look at the concept of increasing network depth. Recall that depth of a network means the number of layers in that network. Typically, when we are designing a convolutional neural network, it is a naive approach or a straightforward approach to simply increase the number of layers in the network and get better performance. Sometimes it works, but mostly there are several drawbacks associated with this technique. First of all, it causes overfitting. The model has learned or memorized the examples in the training dataset and does not perform well on the unseen test dataset. That means the model is not generalizing well. Secondly, such technique leads to increased cost. It takes more time, and more memory and more CPU or GPU resources to train a deeper model. So it will consume up your resources. Thirdly, it leads to the famous vanishing and exploding gradient problems. To understand this, essentially, training a model is simply updating weights of the model. The weights of the model are updated with the help of gradients. If the gradients become too large, then the weights of the model will fluctuate and become volatile. That means that the gradient is exploding and the model is getting unstable model, and it is termed as the exploding gradient problem. On the other hand, if the gradients become too small, that is the vanishing gradient problem. That means that the weights are not updating anymore and the model is stuck. That is, model is stuck. This is called the vanishing gradient problem. Both these problems are resolved by advanced architecture techniques instead of simply increasing the depth of the network. So let's move on. The degradation problem was the motivation behind the development of the ResNet architecture. This problem models or explains the relationship between the depth of the network and the performance of the network. Look at this example graph. The horizontal axis is the depth of the model or the number of layers in the model, and the vertical axis is basically the accuracy, which is a measure of the performance of the model. If we increase the depth of the model, typically the accuracy will also increase. But that is only up to a certain point. Let this be the point. After this, the accuracy will either converge or it will decrease, but it will not improve anymore. Remember that increasing depth causes or requires more resources, more GPU, more CPU, more memory, and more training time. So, if even the accuracy converges, we are still wasting a lot of resources. So, what if we have a better architecture that can work within this depth, and we do not need to increase the number of layers? ResNet is such an architecture. So let's have a look at what ResNet actually is. A residual neural network is made up of residual blocks. Here you can see a comparison between how the convolutional layers are structured in a typical convolutional neural network versus how the convolutional layers are structured in a residual block. In a typical CNN, the convolutional layer is stacked next to the previous layer in the network. This layer is stacked next to the input and this layer is stacked next to the previous layer. Let X be the input to the layer and let this be the output. The only path from the input to the output is through the layers. If f is the transformation that is applied by these two layers to the input, then f of x is the output of the network. Now look at the residual block. The difference is this connection. The connection, an additional connection from the input to the output. This is element wise addition, and the connection is called skip connection. This addition x plus f of x is here, is element by element addition, and an element by element addition is possible only when the width of x equals width of f of x and the height of x equals height of f of x. What if these two layers are changing the height of the x or the width of the x, and the dimensionality of f of x is different from x? So to solve that problem, we can multiply x by a weight matrix. That is, a weight matrix is applied on x here, and it becomes wx. It is common to write it as h of x. Essentially, typical CNN block is learning f of x, whereas this block is learning f of x plus wx. W applied on x. An important point that this residual block has two convolutional layers. It is possible to design our own residual blocks with 3 convolutional layers or more. In case of 3 convolutional layers, residual block looks like something: input, layer 1, layer 2, layer 3, and then the skip connection. And the ResNet 34 and the ResNet 50 are two common variants of the ResNet architecture. I have drawn the architecture of both these models here and compared them. First of all, both these models have a convolutional layer in common. This is a convolutional layer with filter size of 7 by 7, 64 filters, and a stride of 2. Then both have a max polling layer in common, a 3 by 3 filter size, and a stride of 2. After that, look at these square brackets. This means a residual block with 2 convolutional layers. First one with 3 by 3 filter size and 64 filters, and the second one with again 3 by 3 filter size and 64 filters, identical layers. This means there are 3 such residual blocks stacked next to each other in this portion of the ResNet 34 architecture. However, in ResNet 50, the residual block, these square brackets, has 3 convolutional layers. The first one with 1 by 1 filter size and 64 filters, the second one with 3 by 3 filter size and 64 filters, and the third one with 1 by 1 filter size and 256 filters, and such a residual block occurs 3 times. Now, in the next portion, the residual block is almost the same as the previous one, except that the number of filters multiplied by 2. Same case here. And these residual blocks now occur 4 times in both ResNet 34 and ResNet 50. Again, the same thing, that the residual block is almost the same in the next proportion, except that number of filters is again doubled, and the residual block is now occurring 6 times. And here the residual block is occurring again 6 times. The number of filters is doubled. Same case in the next portion. So that means that 3 plus 4 plus 6 plus 3, that is 16. 16 residual blocks, and 16 residual blocks for this one too. 34 means there are 34 layers. You can count them, they will add up to 34. And 50 means 50 layers. You can count them and they will add up to 50. This average pooling layer, it aggregates the features in the previous layers and then passes them to the fully connected layer. The fully connected layer has up to 1000 units. Up to 1000 units. This number corresponds to the number of categories or the number of class labels in our data set. Finally, there is the softmax layer. It converts the output of the previous layer into probabilities. It is an activation function. Now, there are other possible ResNet architectures that we can design. Some common ones that have been designed are ResNet 18, ResNet 101, and ResNet 152.